So we're presenting the breadboard project, and we wanted to give an evocative name, so we're calling it, or I'm calling it, the Crisscross Forge. We spent a lot of time stuck on thinking about a demand meeting application, because that is usually the difference between whether or not a proposal is forgotten by the next day, or maybe it has a chance to be thought about later on. We got excited about the concept of a custom deliverosome that we think would have tremendous demand from the biopharmaceutical industry. There's a lot of interest to be able to create custom compartments that are loaded with very high density of many distinct cargo, RNAs, proteins, etc. And then you could also imagine decorating with targeting ligands with controlled spatial orientations, other fancy things like logic-gated release. So you just release only with the correct tissue type. Just want to reiterate, this is not a competitive method with architectures 1 or 3. It's complementary. Our feedstocks are not molecular in size. They're macromolecular in size. This is a complementary method. Background material, there's been work in the field on making DNA nanostructures that are decorated with proteins. We're talking about something similar, but we're going to be getting rid of the DNA. The DNA is just a temporary scaffold, and we're creating a device that can do multiple turnover. So here's the architecture based on the crisscross origami polymerization developed by Chris Wintersinger, Dio Minov, and Anastasia Ershova in the lab. It works really well in creating lattice points that are spaced about 14 nanometers apart, and that's where we will be loading the different macromolecular components as a starting point. And so those components will be too far apart to actually interact with each other. And then in the next step, we would actuate this grid. After we decorate, we'd actuate it to collapse. And there's precedent for this in the DNA nanotechnology field of introducing in cinched strands to mechanically collapse an object like this. So you can see a couple of examples from the literature. The next step is then we would cross-link the guests along the y-axis. And then if we re-expand the crisscross lattice, then now there's a mismatch. The mechanical mismatch can power the release of the cross-linked protein guest network. One more complication is that in order to get compaction in the x-axis, we actually also have to introduce some rubber bands that we can furthermore cinch, but this is another detail to be worked out. So it's kind of like, I'm not sure I should use a violent analogy. It was like cocking a shotgun. So you're basically loading the protein, and then you're retracting them, and then they pop off. Maybe you guys can help us think of a more peaceful analogy. So contract. Maybe somebody wants to talk about the advantages of this implosion expansion.
Sure. I mean, some of the things that are nice about this method is that a lot of the components we need for it are things that are already working in our field. So we can assemble these like breadboards like based on the crisscross origami slots. There are a lot of methods for doing that actuation. We had a few listed on the previous slides. So like the actual assembly seems totally feasible. And depending on what the applications are, like the fact that we're starting off with a bigger lattice would allow us to spatially segregate components, like maybe we don't want them interacting prematurely, so there adds an additional layer of control in this method that might be harder with other strategies. And by controlling that actuation, so like, for example, the cinching, we can make it like different dimensions, so we can like control the spacing between different components on demand using the same breadboard architecture. So potentially very versatile compared to other approaches. And yeah, like if we combine it with different guests, that allows us to make different sizes. Yep, I feel like that covers all the points here. Unless you have.
I only have one. I think you already touched on it, but I think whenever you have something that where the individual components have been worked out separately, having something that's mostly a systems engineering problem rather than a develop many new capabilities and a systems engineering problem is appealing.
And then the most important thing is why do we actually want to do this? What's that big demand meeting application? So maybe Jacob, I think you were working on this, so maybe you could describe.
Yeah, so and this was one of the ideas for this is how do you go beyond something 2D to something 3D? And so if you think of it like traditional origami, paper origami, not just DNA, you can fold along that 2D axis to make something 3D. And the nice thing is that there's been some amount of work already with people patterning viral capsids and bringing them back together and apart. And the appeal of this would be if you were to put these on something that had this implosion and then expansion ability, you could use the tendency for the monomers to want to stick together to fuel the release. Because when this thing folds up, the monomers are all going to interact. They're not going to want to pull apart. And then when you expand it again, you've now popped off your virus in one step. So that's one less process step that you need to figure out. And hopefully as part of this, you could, and this is a lot of hand waving, kind of feed whatever your payload is inside and then recycle your forge and use it again so that you're not limited by the cost of the DNA.
Yeah, key thing is we actually want to stick pumps onto the outside of the capsid to pump cargo actively into the interior, much like lambda bacteriophage does. Use ATP hydrolysis, for example, to power that. And I think we've gone over time, so maybe this is a good point to stop.
You still have about a minute almost. Well, I guess it's more,
Well, we're
more,
really
more 30
awesome.
seconds.
You guys should remember that we're really awesome. That's
Well, this is the important stuff, though. Tell us what needs to happen.
Yeah, so kind of a couple of things that we listed out, thought about was to what needs to happen in the sense, what are the forge properties that we need and what are the challenges that lies in front of that. So we have to decide a forge material, which is kind of semi-rigid so that the feature, if a foldable feature is maintained. And also thought about, the ways, we have to figure out a way to incorporate these pumps onto this forge material so that it can either catalyze substrates inside the entire assembly or it can pump the deliverable cargo when it's needed. And this pump has to be having an active transport system so that it doesn't do it without a prompt.
All right, we can go to Q&A now, and hopefully we'll get a bit to what needs to happen in the discussion prompts as well. Any questions or comments so far? Yep.
So, what chemistry would you use to conjugate the proteins? Just protein interface or something else?
It's agnostic, so it'd be compatible with non-covalent connections. So we're inspired by viruses. We know that there are viruses like lambdaphage, bacteriophage. It uses non-covalent reinforcement with the kind of wall thickness to impart resistance to deformation. Other viruses like HK97 use covalent chemical cross-linking in order to augment the mechanical strength. So we would be open, this architecture is open to all those possibilities.
Right, so you need to make sure the energy to rip apart the proteins is larger than the energy to rip apart the strands.
Correct. And maybe that'd be good motivation to go covalent.
So to me, one of the appealing things, so at least molecular manufacturing often get hung up on the issue of scaling. And so to me, one of the appealing aspects is, as we heard yesterday, you can make these crossbar lattices very big and grow them a lot. I was wondering if there, in addition to just growing the lattice, if there were any other aspects of the proposal that would not scale as well, or could you just do this on as sort of arbitrarily large lattices?
Well, we're working on trying to push the limits of the size that we can grow these. There's always going to be some physical limit, but we don't know yet.
But nothing in addition to just growing the lattice. In other words, the lattice is the limit, as opposed to anything else in terms of actually using the lattice, like the contraction and
I would say this is an ambitious proposal. There are many potential pain points.
The lattice is the limit. I love it.
How often can you recycle the forge template and have, how many cycles can it go before it starts to wear down? And that's, I mean, anything with degradation is a little bit of an open question.
We also discussed ideas of further turtles on top of turtles. So could we make a forge that builds a protein machine that's actually going to build the deliverosomes? So if you have machines that build machines that build machines, then that allows you to, that level of nesting could build you, in theory, greater throughput if your original material is limiting.
Thank you.
So
Awesome.
One practical thing that happens with one practical thing that happens with therapeutic manufacturing is that it's surprisingly like affordable to make large amounts of materials like DNA. We can buy grams or even larger quantities of materials at reasonable costs for pharmaceutical applications, and then this would of course have multiple turnover type properties, so it's not that expensive. Something that has surprised me, like when going to manufacturing, though, is the necessity of manufacturing at high concentration. And then, when we have things at high concentrations, sometimes they don't quite work the way that we expect. And the downside of not manufacturing at high concentration is that at normal, like DNA nanotech concentrations, your manufacturing facility, if you really think about like scaling it up to reasonable production volumes, they have to get very, very, very large, the volumes that you end up handling. So that's like a more practical consideration, but it's always like, you can figure out ways around that, I think.
Okay, we have a final question from Irina, and then we'll do the discussion prompt.
Yeah, thank you. I was just wondering, so maybe my bad, yeah, maybe I just didn't grasp. What is the demand you're trying to meet here?
The demand meeting application is compartments
Yeah.
with controlled stoichiometry of very high density, loading density of valuable cargo with targeting material ligands on the surface and also logic gated release.
Yeah, so something that liposome cannot do, or...
Yeah, something that's like your ultimate dream of converting a virus into a delivery vehicle.
Okay, yeah, thanks.
Okay, well now you can stay right here if you want to. I just want to make sure that we get to a few of the different discussion prompts. First, I think a few bits that we may not have gotten to during the presentation are basically like, what would you be doing to make it happen? I think you briefly touched on it, and then is there anything, that you would be doing with the 5K development grant, if at all?
Well, I think we would try to do a prototype to create just first steps of showing that we could attach some kind of building block to the lattice points, that we could contract, cross-link, and then release. I think that would be a good first step. In terms of development grant, I mean, there's a lot of fuzzy details here, so funds for some follow-up meetings. I'm not sure exactly what the 5K would go to, but something to do with the follow-up meeting.
Good.
Coffee and snacks.
Okay, wonderful.
Coffee and snacks.
Yeah, that's a good.
Coffee and snacks. Then we a few questions for you guys. Is there something that you thought was particularly exciting about the proposal, or something that is really missing, like a thing that you would want to slot in if you could, or something that they should still be taking into account?
Was it the proteins you would have DNA cross-linked to the proteins and that would dock to the place?
That's what I was thinking. There would be DNA adapters that could then be degraded or released afterwards. But the DNA ultimately is just a temporary scaffold.
And
Is the idea, would all the protein units be the same? Is that the idea?
Yes, the idea is to be able to have a mixture of kind of nondescript proteins controlled by the lattice, but then at site-specific places, you could put distinct molecules, so different kinds of pumps, different kinds of ligands. So the beauty is you can combine very boring particles that serve a structural unit and very functionally useful ones in design locations.
okay, and final one, is there anyone else who should be working on this that they may not know? Is there anything that you could be providing in terms of advice? No? Okay, well, thank you.
Was that?
Rely on you for that, for the red teaming. Thank you guys, wonderful.